So today's lecture on vectors, matrices, and tensors. So you've already gotten your first exposure to matrices and vectors when we were talking about solving systems of equations and how that related back to the central topic of the finite element method. Back in the lecture that we hosted on Wednesday, we presented exactly this idea of assembling a system of equations that consisted of this so-called stiffness matrix and arranging different vectors of unknown nodal displacements and applied external forces in these vectors. And we could solve that resulting system of equations to determine what the unknown nodal displacements were by basically making some substitutions and some rearrangements, solving for the individual nodal displacements, and then plugging things back in to recover other things like what's the internal force in each member, what are the reaction forces acting on the system. And it all hinged upon this notion of solving a system of equations, setting it up, solving it. So really, I want to kind of take a deep dive on this subject of looking at how we set up systems of equations and how do we interpret these kind of structures that we've come up with, these, vectors and matrices, and provide a few preliminary definitions that'll carry through for the rest of the lecture and for the rest of the class, in fact. So without further ado, I do want to actually provide you with some supplementary resources. That you can't rely entirely on me to understand these concepts. And I think there's some really excellent resources out there, including I'll point to 3 Blue, 1 Brown. If anybody has heard of this particular, it's a YouTube channel that presents a lot of really cool visualizations of mathematical concepts. And in particular, the channel run by Grant Sanderson includes a whole video series specifically devoted to linear algebra. And it presents all these concepts in a very graphical way that provides, very nice physical intuition behind the concept. So as a supplement to today's lecture, I'll encourage you to go maybe check out those videos, review them, reinforce your own intuitive understanding of these concepts, how they relate back to kind of the physical interpretation of what is a vector and having different perspectives on what that means. So go ahead, check that out. We won't go through some of these videos in class, but that'll be kind of an outside of class activity. So now I want to get to this subject right off the bat. What are vectors and matrices to start out with? And I'll add in another category. I'll add in this other thing I'll call a scalar. And a scalar is really nothing more than just a single number. And usually if I'm denoting a scalar, usually I'll denote it with this kind of maybe lowercase letter or something, non-boldface, and it will belong to the set of all possible real numbers. A real number could be 0, it could be 3.1415, it could be 2.57, it could be -2 or whatever. Real numbers are basically any number that you can think of on the real line, ranging from -infinity to +infinity. Fair enough. So the scalars are just single numbers, but with scalars, we can also arrange them in interesting ways, like in the format of a vector. A vector is really just an array of scalars, basically. And typically, the way that I'll denote vectors in this class are using usually lowercase letters put in boldface. And if you yourself are working through a homework problem and maybe trying to write something down, and maybe it's not clear how you would embolden a particular character on a page or something, if you were writing it, the typical convention for written notation in denoting vectors is usually, there's a couple different ways you can do it, but you can either do a nice little undersquiggle. That's kind of what I do. Some of the physicists will sometimes put a little arrow over the top of it. So it's whatever you prefer, but there are different ways that you can kind of make it clear that I'm talking about a vector here as opposed to just a scalar. If it's just sitting there without any annotations, then on the page, that's kind of what a scalar would look like versus a vector. And then finally, a matrix, which is basically a two-dimensional array of numbers. And it doesn't necessarily have to be, equally proportioned in, its 2 dimensions, potentially. As in the case of this example, a matrix could be basically some array that maybe has some number of rows and some number of columns, and the number of rows and columns don't have to be equal to each other. Canonically, I will denote matrices using uppercase letters, put in boldface if I'm kind of typing it up on these notes. And if you're trying to write it on a page, you'd use uppercase letters and do some kind of undersquiggle or something like that. Or if you like, you can also put a little arrow on top of it too. I think it makes it a little bit more clear to put it down here, because you might put other annotations on the top of these things and decorate it with little hats and funny, propeller beanies or whatever else you want to put on them. So in general, that's kind of the notational approach that we'll take to defining scalars, these kind of single numbers, vectors, one-dimensional arrays of numbers, and matrices, two-dimensional arrays of numbers. And I'll also adopt this notation of defining what spaces or sets do these different quantities belong to. Typically, if I'm talking about a scalar, it belongs to the set of all possible real numbers in general. Vectors basically belong to Rn, basically, the space of vectors in some space of dimension n. So if there's some vector that maybe has, let's say, n possible entries in it, arranged in this kind of vector format, then really, if I'm saying, the space of all vectors with n entries or n components, then really I'm talking about, a very specific subset of vectors. Same thing if I'm talking about matrices, I have to be precise about the size of the matrix. So if I say some matrix that belongs to the set R to the m times n, what I'm talking about is the set of matrices that are basically of size m rows by n columns. So that's kind of just notationally how I'm going to denote these different kind of concepts. And to give you a little bit more intuition behind it, and to explain a little bit more behind how we're going to distinguish particular entries in vectors and matrices, I'll introduce this kind of indexing scheme or index notation to denote how I will choose to identify a particular component that might lie within some specific vector. So a vector written in boldface, which lies in Rn, for example, will have some number of components, n components in particular. And each one of these components, I can distinguish by basically using some kind of subscript index, usually kind of denoted like this. So if I'm trying to identify the second component of this vector, let's say, a sub 2, I can be particular about this and say, well, I want to look at a sub 2. What value is a sub 2 in this particular, in this case, a three-dimensional vector? Same thing, if I want to distinguish a particular entry in a matrix, I can index that matrix entry using two sub-indices, I and j, where I and j can range over the number of rows in this matrix and the number of columns. So if I wanted to distinguish this entry, a sub 1, 2, that would refer to the component in this matrix that lies in the position of the first row and the second column. And you can kind of interpret how that would generalize in other contexts as well. So other interesting things to note about the geometric interpretation of vectors in particular is that certainly if you're familiar with vectors and how they apply to different domains of mechanics, you probably already well understand that vectors have kind of a physical intuition behind them, particularly if we're talking about vectors that lie in two-dimensional or three-dimensional space, things that we can easily visualize. So for example, a two-dimensional vector, let's say A, might have two components, which characterize its position, let's say, in some two-dimensional space. And I can represent this vector as basically some kind of arrow, which starts at the origin of some kind of two-dimensional space, and which can be drawn such that its length measured relative to the first dimension, let's call it x, or if you like, I can also call it x sub 1. Its length in that dimension corresponds actually to this first component of the vector. So the vector A has really two components, A1 and A2, and its projected length on each of these two different coordinate axes in a two-dimensional space precisely corresponds to those two components. So there's a nice physical intuition behind vectors in these kind of lower dimensional spaces, but it doesn't necessarily mean that we're restricted to strictly two or three-dimensional spaces. The number of entries in a given vector n could be bigger than that. It could be 100, it could be 1,000, it could become arbitrarily large. And in general, if you're solving systems of equations, and you want to represent things in terms of these very large vectors, you kind of need to generalize the concept to arbitrarily dimensioned spaces. Now, there's another kind of useful particular vector that I'll define, which I'll call the zero vector. It's a special case of a vector that basically has all of its components equal to zero. There's an analogous definition for a zero matrix, which basically says it's a matrix whose entries are also all zero. But the zero vector, I think, is a little bit more interesting and has a little bit more utility in general. So just kind of a few preliminary definitions there. So far, how are we doing? Does this kind of all feel like review to you, and kind of maybe just squaring some of the fancy mathematical terminology and notation in your brain and kind of connecting the dots a little bit? So, all right. Feel free to kind of suggest we speed up or slow down, depending on how you're feeling as we kind of go through this. All right, but that's the basic idea behind, vectors, matrices, and scalars. And in general, there's different ways that we can have these different quantities interact with each other. Certainly, there's scalar multiplication, basically taking a single number and multiplying it by another scalar, multiplying a scalar by a vector, or multiplying a scalar by a matrix. And a scalar, the name of scalar kind of implies that really all we're doing is we're taking that quantity, let's say a vector, and we're scaling it. We're basically taking all the components of this vector, let's say B, and we're just increasing them or multiplying them by this scalar quantity A. So if I were to look at the individual components of this resulting vector C, that would result from taking the scalar multiplication of A times the vector B, really the individual components of the vector C indexed by I would be obtained just by taking the individual components of B and multiplying each of them by this scalar A. And this idea generalizes, obviously, to the case of multiplication between a scalar and a matrix. All it requires is just recognizing that we just take each of the individual components of this matrix B, multiply by A, scale them by A, and then that gives us the individual components of the matrix C. All right, fairly straightforward. Nothing fancy here. Hopefully nothing new also. Other kinds of concepts that you're probably familiar with is this notion of the dot product between vectors. And, I don't think I need to tell you, but maybe you can tell me, what exactly is the dot product? How do you determine it? What is it? Well, I have some of it here, but go ahead. Yeah.
every every row from the first part, it would be in column in the second, and you just add them all together.
Yeah, I think in essence, you're trying to take two vectors. If we're talking about a dot product between vectors, sometimes this is also called an inner product. But basically, dot product, inner product, they mean the same thing. But in essence, I think you're on the right track. The dot product between two vectors produces a scalar, a single number, right? So if I start with two vectors, they have to be the same length. In order to compute their dot product, I basically take the summation of the products of the individual components of these two vectors. So in other words, let's say I have two vectors A and B. I can compute their dot product by basically summing up A1 times B1 plus A2 times B2 plus so on and so forth up to AN times BN. And I just sum them all together to get a single scalar number. And that's the dot product, fairly straightforward. And the physical intuition behind the dot product is, in a two-dimensional sense or a three-dimensional sense, usually the dot product kind of gives you a sense of how closely aligned are these two vectors. In particular, if two vectors, let's say in a two-dimensional space, are perfectly aligned with one another, then the dot product will be, some kind of large or positive number. If they're perpendicular to one another, the dot product tells us that, oh, well, these two things aren't aligned at all. They're kind of like pointing in mutually orthogonal directions. And the resulting dot product between those two perpendicular vectors would effectively be 0, in fact. If they were pointed opposite to one another, then there'll be a large number, but it'll be a negative number, basically. So that's kind of the physical intuition behind the dot product. It gives us a measure of how close are two vectors to one another. And in fact, this notion of an inner product or a dot product can be generalized to matrices as well. This might be a little bit new if you haven't seen this before. But I'll choose to adopt a notation that looks a bit like this. If I have two matrices, A and B, and again, these two matrices have to be the same size. We'll say that each one of them has m rows and n columns. The idea here is to do kind of a similar thing to how we define the dot product for vectors. In this case, though, we're going to consider it as basically just the summation of the products of all the individual components of each of these two matrices all summed together. So in other words, if I wanted to take the inner product between these two matrices A and B, which will result in a single scalar number, all I have to do is sum up A11 times B11 plus A12 times B12, and all for basically all of the individual entries ranging over all of the rows and columns in each of those two matrices. So fairly straightforward. There is some utility for this, but we probably won't get to exactly where that ends up being useful until a little bit later in the class. All right, so that's the inner product. And also, the nice thing about the inner product is that it also provides us with a measure of length. If we're talking about a particular vector, A, let's say, which lies maybe in this two-dimensional space, we can also measure things like what's the length of this vector, or what's its magnitude. And usually we compute that just by saying, well, let's compute the sum of the squares of all the components of that vector, right? That's probably something that you're familiar with. The sum of the squares of some kind of vector gives us the length of that vector. And in general, it kind of relates back to this notion of the Pythagorean theorem. A squared plus B squared equals C squared, right? Well, that's kind of essentially what this thing is doing. If we're computing the length of some vector, sometimes also called the norm of this vector, really all we have to do is take the sum of the squares of these two things and then actually square root it, which in effect is actually defined with the aid of this dot product thing. So if we take A dot product with itself and then take the square root of that, in fact, we recover the length of that vector, or we recover the norm of that vector. A similar definition holds for defining some kind of norm of a matrix. And in fact, there is a particular norm defined for a matrix called the Frobenius norm, which looks very similar in form, but instead uses this notion of this matrix inner product, or the Frobenius inner product. So basically just the sum of the products of the individual components of this vector or of this matrix all summed together, and then take the square root of that thing. And it'll give you sort of a measure of the size. The notion of length in the case of matrices is a little bit less well defined. And there isn't as much of a physical intuition, but as is the case in a lot of domains of mathematics, you know, these concepts can be abstracted and played around with in kind of weird ways. All right, so that's the notion of norms. Other things that we can do with vectors. You're probably well familiar with this notion of the vector cross product, right? Which also has a nice physical intuition. Suppose I have two vectors, A and B, and I want to point out that really the definition of this cross product is really only valid in the case of three-dimensional vectors. So if I'm considering two vectors A and B that lie in some kind of three-dimensional vector space, then really I can define the cross product between these two things by basically taking some kind of weird products between the different components of A and B. And you know, there's obviously this formula that you can follow to compute what are the individual entries of this resulting cross product vector. But the intuition behind that actual operation and what it represents can be thought of in the following way. Suppose I have these two vectors A and B. They exist in some three-dimensional space, kind of like shown in the figure here. And if I take the cross product between those two vectors, using the right-hand rule, what that cross product will give me is a new vector that is perpendicular to both A and B and whose magnitude or length is actually proportional to the area spanned by this kind of parallelogram that's formed between those two original vectors A and B. So it's kind of interesting. There's some geometric interpretations to be had with the cross product in 3 dimensions. And so that's kind of the intuition behind it. But it takes 2 vectors, gives me a new vector that's perpendicular to the original 2, and which is proportional to the area of the parallelogram between those 2 original vectors. Now, there's also this other kind of funny thing, the outer product. We talked about the inner product, the dot product between 2 vectors. The outer product is kind of another concept. We've talked about, products between vectors that give us back a scalar. That's the dot product. We've talked about products between vectors that give us back another vector. That's the cross product. Now, the outer product is a type of product between vectors that gives us back a matrix. And the way that it works is actually fairly straightforward. Basically, you compose the entries of this new matrix, given these 2 vectors, and using this kind of funny, circle with a cross through it symbol representing the outer product or the dyadic product between these 2 vectors. And the resulting matrix that's formed between these 2 vectors using the outer product is precisely something that looks kind of like this. The individual entries will kind of have specific components that look like AI times BJ. So if I wanted to know what is the resulting component in this kind of matrix C formed by this outer product, and let's say what's its entry in the first column and the second row of this resulting matrix. I can go here and I find that it's the product of A with subindex 1 corresponding to the first row of this matrix and times B sub 2 corresponding to the second column of this matrix. So it's really just kind of the entry-wise product of these different things, but with different permutations and entered with different kind of combinations in each of the different components of the resulting matrix. So kind of cool. So we can do all kinds of things with matrices and vectors and kind of get different resulting quantities out of them using these different interesting operations. All right. Now, other things that we can do now in combination with vectors and matrices. We're working towards our original goal of kind of trying to represent systems of equations. Okay, so we talked about products between scalars and other kind of scalars and vectors and matrices. We've talked about products between vectors to give scalars and vectors and matrices. What about products between matrices and vectors? And in particular, the matrix vector product, sometimes denoted like so, where basically I'm using still the dot symbol and these kind of like uppercase and lowercase symbols to represent matrices and vectors, just to kind of square things in your mind. The idea is, in order to compute the product between a given matrix and a vector, I can do something similar to the way that we defined the dot product, if you remember. The dot product was kind of like a summation of the products of individual components between 2 vectors, right? Well, we can kind of do a similar thing in defining this notion of matrix vector multiplication. And we can write out how we would do that in terms of summations and multiplications between the different components here. Effectively, what we would get out of this operation, though, is some other vector. So if I have a matrix A multiplied by some vector B, what I'll get back is another vector which has basically the same number of components as I have, in this case, rows in the original matrix M. And it's probably easier to think of things in more graphical terms. So consider this particular example where I have, let's say, a matrix that has dimensions 2 rows, 3 columns. Let's say I have this vector B with 3 entries arranged in the format of this kind of column vector, if you like. And the idea is that the resulting vector that appears from this matrix vector product, it can be computed in an entry-wise sense by supposing that, let's say, C1 is really just the result from taking the inner product or the dot product between the first row of this matrix and the column of this vector, basically. So that is what gives me this first entry C1. It's just this row dot product with this column. Same thing, C2 would just be this row dot product with this column. And you can kind of proceed and generalize that idea to, matrices and things of other more general sizes. The notion of matrix multiplication, or in other words, multiplication between two different matrices, kind of follows a similar format, but generalizes this idea. And it supposes that maybe I don't just have, these columns or these column vectors as strictly vectors. Maybe they themselves are implicitly, matrices, but degenerate matrices that have, in this case, two rows, but only one column. Or this vector, it really has, three rows and one column. So if I wanted to think of vectors as just a special case of matrices that happen to have just one column, I can also generalize this notion of matrix vector multiplication into the format of how I should interpret and define this notion of multiplication between two matrices. And the way that I can do that is by just saying, if I want to know, let's say, what's the resulting matrix that would arise from multiplying these two matrices A and B together, I can determine what's the specific component or entry in this kind of resulting matrix, let's say C12, by basically, again, using the dot product. This entry C sub index 1, 2 is really just induced by the inner product or the dot product between row 1 of the first matrix, dot product with column 2 of this second matrix. Now, you can recognize that there has to be some consistency here. The number of columns in this matrix does need to match with the number of rows in this matrix for that inner product operation to be well defined. If those two kind of quantities, if this row didn't have the same number of entries as this column, then you can't take a kind of matrix multiplication approach to solving that problem. It's just not a well-defined operation. So anytime you have a multiplication between either a matrix and a vector or a matrix and a matrix, you kind of have to make sure that this index, or in other words, the number of columns in this matrix is equal to the number of rows in the corresponding matrix on the right-hand side of that operation. So just a little bit of a subtlety. The idea also generalizes to this notion of multiplying a vector times a matrix on the right-hand side. In the last slide, we were considering kind of the opposite, trying to do something that looks like this. Take a matrix and multiply a vector on the right-hand side of it. But if we take this generalized notion of, matrix vector multiplication just being a special case of matrix multiplication, then we can also define the same thing for left-hand multiplication of a vector times a matrix by supposing that really, this resulting vector on the left-hand side and this vector are not arranged as columns or column vectors, but rather they're arranged in the format of these row vectors. So that's really the only change in perspective we have to take if we're going to define this alternative description of matrix vector multiplication, where the vector is on the left-hand side of the matrix. All right, so that's fairly straightforward, but the notion of applying the same concept of take this row, multiply by some column in the thing on the right-hand side to give me a particular entry in this resulting kind of quantity on the left-hand side, that all follows through. So again, individual components, let's say, the component that lies in the second column of this, row vector is simply the inner product or the dot product between this sole row of this vector multiplied by the second column of this matrix. All right, straightforward. And again, we have to have consistency. There has to be the same number of components in this vector, 2 in this case, as there are rows in this matrix. Okay, so that's matrix vector multiplication and all those different things. Now that we've defined these different operations between these, notions of vectors, matrices, scalars, let's take a closer look at matrices in particular and some special cases of matrices that will be of interest to us. So in particular, let's define this notion of a matrix transpose. In particular, if we took this example of a matrix, that same example we've been working with, 2 rows, 3 columns, arranged like so with the components shown here. If I wanted to compute the so-called transpose of this matrix, all I have to do is take the original rows of this matrix and then kind of flip them such that what were originally rows in this matrix are now columns in the transpose of this matrix. So the transpose operation defined for matrices could also be applied to vectors. Simply takes the original rows of this matrix and then flips them such that now they're defined as the columns. So if you like, the way of looking at this from kind of an index component view of things is that the entries of the transpose of a particular matrix indexed by I and j are basically flipped. So if I had some original matrix that was indexed by rows I and columns j, in order to determine its transpose, all I have to do is kind of like permute those two indices. Kind of straightforward. All right. So that's really the geometric interpretation of the transpose. So other interesting things that we can apply this to. Usually, not always, it's generally true that matrices don't have to have the same number of rows and columns, right? But there are certain special cases, and in fact, certain important cases where we want to consider square matrices. And that's simply matrices that have the same number of rows and columns. So for example, this 3 by 3 matrix is an example of a square matrix. And in particular, we can look at other properties of square matrices, namely the property of symmetry. If I have a square matrix, same number of rows and columns, I can assess, is this matrix symmetric? And by that, I mean, are the individual kind of off-diagonal entries taken just by permuting these kind of two sub-indices, are they equal to one another? Or in other words, is A12 equal to A21? Is A13 equal to A31, and so forth? And if I can evaluate that and assess, is effectively the transpose of A, taken by basically just flipping those individual entries, is the transpose equal to the original matrix itself? And if that's true, then effectively I can say, yes, this matrix is symmetric. So as long as those off-diagonal entries are the same, or in other words, if I permute these two kind of indices and find that their permuted individual components are all equal to one another in an entry-wise sense, then I can say the matrix is symmetric. Okay, fairly straightforward. Other special cases of matrices that are interesting and useful to us. The identity matrix. This one's pretty easy. It is also a square matrix. It is also trivially a symmetric matrix. And also, quite nicely, it's very simple. It basically has all zeros on the off-diagonal components of the matrix, and the only non-zero values in this matrix are along the diagonal, basically. And in fact, all of those diagonal entries are just equal to 1. So in a matrix format, I can write it like this. If I were to write it in terms of describing its individual components, however, it's usually not the case that we say, I sub, ij. Typically, the identity matrix is denoted with this kind of capital I symbol. But when we're referring to the specific components of this identity matrix, usually we reference those indices using this kind of funky delta symbol. And sometimes people call this the Kronecker delta. But basically, it's just nothing more than a representation for these kind of indices in this identity matrix. So in other words, if I and j are equal to one another, or in other words, if I'm talking about the diagonal entries of this matrix, all of those diagonal entries should be equal to 1. Otherwise, if I'm talking about any of the other off-diagonal components, where the indices of any particular component in this array, I and j, if they're not equal to another, then basically those entries are equal to 0. Certain other special properties of the identity matrix are that if I take the matrix vector product of the identity matrix times any vector, what I get back is the original vector. Fairly straightforward. And if you like, you can kind of represent how that would appear in this sort of index representation of multiplying the individual components of the identity matrix represented using the Kronecker delta symbol and expressed through this kind of summation operation. Okay, same thing if I take the matrix product between any matrix A and the identity matrix. I'll get back the original matrix. And it's actually quite nice. So that's the idea behind the identity matrix. It basically preserves the original definition of whatever matrix and passes it through unscathed, in other words. Okay. Other properties, other definitions of matrices that you may have encountered. For any square matrix, we're still on the subject of square matrices. There are two operations that are worth knowing. The first is the trace. The trace of a matrix is really nothing more than the sum of all the diagonal entries in that matrix. So in other words, if I were talking about the identity matrix, it would be the sum of all the ones along the diagonal, and the resulting value of the trace of the identity matrix would just be equal to n. However, if I were talking about some more general matrix, it would be more like the sum of A11 plus A22 and so forth all along the diagonal. Sum them all up, and that's the trace. The other quantity, the other kind of thing that's worth knowing, a special operation only applying to square matrices, is this notion of the determinant. And the determinant is really kind of a funny thing. It's kind of hard to express notationally in a generic way, but you've probably seen it and used it in other contexts and applied it to maybe 2x2 matrices or 3x3 matrices. In the case of a 3x3 matrix, as shown in this example, the determinant has this kind of interesting interpretation. It's basically the sum of all the products of these kind of like diagonal terms, all summed together, minus the product of all these kind of diagonal entries. So in other words, these kind of collections of terms precisely correspond to those sort of diagonals as shown, and these kind of diagonals are precisely these. So A11 times A22 times A33, the product of all the diagonal entries precisely corresponds to this kind of diagonal. A12, A23, A31, that's this term here, but also this term, A12, A21, A33. That's this one. So in effect, we're taking either the sum of any kind of like downward sloping diagonals minus any kind of backward sloping diagonals formed between different combinations of these kind of diagonal combinations of entries in this square matrix. And you can kind of take these two columns, paste them over here if it helps to kind of visualize and how to figure out some of those computations, but that's the determinant. So two different operations specialized to square matrices, trace and determinant. And the determinant in particular is actually quite useful in assessing certain properties of other square matrices. And the most notable property of square matrices is whether you can invert it or not. So probably the most important concept that we'll walk away with in today's lecture is this notion of invertible matrices and taking the inverse of a particular matrix. So suppose I have a square matrix, A, with n rows and n columns. Its inverse is defined in this kind of unique way, such that if I take the matrix product between some matrix A and its corresponding inverse, what I'll get back is precisely the identity matrix, the n by n identity matrix in this case. And it actually happens to be the case that whether I take the matrix product of A times A inverse, or if I take A inverse times A, doesn't really matter. I'll still get the identity matrix back. Now, there is a condition for us actually achieving invertibility of this matrix. The inverse of A is only well-defined if A is invertible. And you can assess whether a particular matrix is invertible or not by looking at its determinant. So if the determinant of A is non-zero, or if you like, if it's greater than 0, it doesn't have to be greater than 0, but in general, as long as it's not 0, then A will be invertible. And in that case, we can kind of do some fun things with it. And in particular, we can solve systems of equations. Before we get to that, there's some other kind of terms that are probably worth knowing. One in particular is this notion of positive definiteness. If we have a square matrix, which is also, let's say, symmetric. So square symmetric matrix, similar to what we considered before, and rows and columns. If you transpose that matrix, you get back the original matrix, so it's symmetric. Now, this notion of positive definiteness of matrices arises by considering what happens if we were to take this matrix and left and right multiply it by some arbitrarily chosen vector v. What I should get back from this operation, after I take the matrix vector product, here I'll get a vector, and that vector dot product with this original vector v will give me back a scalar. So at the end of the day, v times a times v gives me a scalar. And if that resulting scalar is always positive, regardless of what vector I choose, then I can say that this matrix A is positive definite. And there's some implications as to what that really means and the significance of that and why we care about that, but we won't arrive at those discussions until a little bit later. The main thing to know is that if you have this property of positive definiteness, it is a sufficient condition to ensure that a particular matrix is invertible. And there's some other nice aside properties that come from having this property as well. We'll talk about that later. Positive semi-definite matrices almost satisfy the same requirement. The only difference is that basically you'll get a value that's either positive or zero. The key thing here is that if a matrix is only positive semi-definite, then it is not invertible. That's the main takeaway I want you to have. So in general, positive semi-definite matrices, not invertible. Positive definite matrices, definitely invertible. Okay. Now, the last thing that's probably the most worthwhile thing to discuss is this notion of how do we use these kind of tools, these linear algebra concepts, to actually solve problems of interest to us, to solve engineering problems. And the idea comes to this, notion of solving simultaneous systems of equations. And not just any systems of equations, linear systems of equations. Linear systems of equations are specific types of equations that can be expressed sort of like what's shown here, where I have maybe some set of unknown quantities that I'm interested in solving for. Let's say X, who might have multiple different entries that we're interested in. So there might be some set of unknowns, x1, x2, all the way to xn. I can arrange all those unknowns in the format of a vector. And ultimately, if I can express the resulting equations or set of constraints on these different unknowns that I'm trying to solve for, if I can express them in this sort of special way, where each of these equations basically just takes some random constant value times each one of these different unknown quantities, then it turns out I can convert this representation of this system of equations into this sort of matrix vector representation, where all the coefficients, a sub I and j or whatever, I can consolidate into this matrix. The unknown quantities I can put into this single vector, and anything else that's left over, I can shove over onto the right-hand side of this equation that I'm solving, and I can put that in a vector as well. And assuming that there are the same number of rows, or in other words, if there are the same number of equations that I'm trying to solve, and if that same number of rows or equations is equal to the number of unknowns that I'm solving for, so in other words, if the number of rows and columns in this matrix are equal to one another, suggesting that I'm looking at a square matrix, then I have a hope of actually uniquely solving for what these different unknowns are. And in particular, if I'm lucky enough that this system of equations, that this resulting square matrix is invertible, then I can in fact solve for this set of unknowns using this definition for the inverse of the matrix A. And you can kind of see that in a stepwise fashion. If our system of equations can be expressed in this kind of matrix vector multiplication based format, A times X equals B, then I can proceed by just left multiplying the left and right hand side by A inverse. I know that the product of the inverse of some matrix A times itself gives me back the identity matrix. So I can make that substitution. And finally, the identity matrix times any vector gives me back the original vector. So I finally arrive at this conclusion that if I want to solve for x, I basically have to compute the inverse of this matrix and apply it to this right-hand vector b. This concept really has broad utility. Obviously, it applies directly to this notion of solving systems of equations for the finite element method, but it applies in a bunch of other domains I'm sure you're probably familiar with. Now, the last thing that I want to talk about briefly, is this notion of tensors. And really, if you already have a good handle on scalars and vectors and matrices, tensors are really just a generalization of those same concepts, but also a special case. So a tensor is really, all of those different things that we previously discussed. Tensors describe scalars. They encompass vectors. They encompass matrices, but they actually have some special generalizable properties. The first condition is that a tensor can have some variable rank. And rank really just refers to what's the dimensionality of this quantity that I'm looking at. A rank 0 tensor is really nothing more than a scalar. It's basically a 0-dimensional number, a single number, in other words. A rank 1 tensor is basically a vector. It's just a 1-dimensional array of numbers. So in other words, rank 1 tensors are just vectors. Rank 2 tensors are 2-dimensional arrays of numbers. Matrices, the things we've already defined. And we could stop there, but why stop there? Really, the notion of tensor generalizes to arbitrary rank. We could define these weird new objects. We could call things a rank 3 tensor that now has 3 different dimensions. So instead of a 2-dimensional array of numbers, we have this 3-dimensional array of numbers, kind of like a cube or something. And then finally, we can take it all the way up to rank 4. We won't go higher than that. Rank 4 is as high as we'll go. But in general, it'll index over possibly 4 different sub-indices in the case of a rank 4 tensor, as compared to only 2 sub-indices in the case of a matrix, or only 1 in the case of a vector. The other special condition, however, on the subject of tensors is that in general, the range of each of these different sub-indices is constrained. And typically, it only ranges between 1 to 3. So in general, if we're talking about a tensor, a rank 2 tensor, it's always going to be a 3x3 matrix. If we're talking about a rank 1 tensor, I'm talking about a vector in 3-dimensional space. And if I'm talking about a rank 4 tensor, I'm talking about a 3x3x3x3 array, which gets really messy. And how you even conceive of how you would represent that is a little bit vague and, hazy. But in general, those concepts can be, generalized and applied. I think that's probably all we have time for. We'll have to pick up things, not on Monday because we have a holiday then, but next Wednesday. So in the meantime, feel free to visit me in office hours. We'll pick up where we left off next week. All right, I'll see you then. Yeah, it's a matrix of matrices. That's kind of how I think of it, actually. Yeah.